Hi, I'm Andy Gainey of Experilus Software. This is a tutorial for tile-based worlds, my Unity framework for creating and managing game worlds based on discrete tiles, available in the Asset Store. In this video, we will see how to use the framework to create a hex grid world at runtime, and a dynamic mesh to represent that world graphically. We will add mouse picking, using the framework to easily determine which tile is intersected by a mouse ray. Finally, we will use a couple of tile visitation algorithms supplied by the framework, including the A-star pathfinding algorithm, to modify attributes of the world, updating the dynamic mesh accordingly. The bulk of the framework is ideally accessed through code, not directly from within the editor, so expect to see a fair bit of code in this tutorial. Let's get started. We'll begin by importing the framework package into a new project. The full package from the Unity Asset Store includes all example scenes and resources, but it also includes the stripped-down packages seen here to save you trouble after the initial download. We'll drag the tile-based worlds with dependencies Unity package into our project to import it. Now let's dive into the scene. This tutorial won't contain a lot of moving parts in terms of individual game objects. All we really need is one top-level object with a single script to handle all the runtime generation and processing. So we'll create a tutorial game object, for lack of a better name. And we'll create a matching script to go with it. We'll start fresh with the empty script. First we'll add some public fields which we can access in the inspector. We will also need a surface object to describe the overall shape of our surface. This will come from the Experilus.topological namespace, within which a lot of the tile-based worlds framework can be found. Additional utilities will also be found in the Experilus namespace. In addition to the surface, we will need a topology object, which defines the relations among the tiles. Custom attributes will store the positions of each vertex and face, or tile, as well as the vectors bisecting each corner. A dynamic mesh object will be used to create renderable meshes at runtime from the topology and custom attributes. Now we're ready to initialize our world. In our start function, we will create a rectangular hex grid surface, which describes the particular arrangement of hexagonal tiles that we desire. The planar descriptor specifies the overall orientation of the plane and its two axes. The hex grid descriptor is responsible for arranging the tiles in a variety of ways depending on one's needs. Finally, we specify the size of the world pulled from our public fields. We'll save that off to our private surface field. Next up is the topology, plus the custom attributes. The hex grid can be constructed as a manifold, which provides both the topological relations as well as spatial positions of all vertices. The array of vertex positions can then be wrapped as a vertex attribute to give it the full flexibility of that interface. Face positions can be computed directly from vertex positions. We can use functions from the face attribute utility class to help us, in this case calculating the centroids for all internal faces. Similarly, edge attributes such as bisectors can be computed using the edge attribute utility class. This requires both the vertex positions and face positions as input. We will create a dynamic mesh object which will create meshes for the internal faces of the topology, and will contain position, normal, and color attributes for the vertices. The triangulation scheme also needs to be specified, which is responsible for turning each face into a collection of triangles. We will use what I dub umbrella triangulation, where a center vertex is used as the base of a triangle fan, and the first outer vertex is shared between the first and last triangle. An additional ring of vertices will be added to allow us to render a nice border around each face. The triangulation object requires a couple of callbacks. The first requests that we supply the vertex attributes for ring vertices, starting with the outermost vertex moving inward for each ring. Since we have two rings of vertices, we need to supply attributes for two vertices at a time. Outer vertex position is easily looked up in our positions attribute, normal is constant, and the color is that specified for the border. Then we advance to the next vertex. The position of the inner vertex is based on the outer vertex, but offset in the direction of the bisector that we previously computed. The normal is similarly computed from the position of the vertex relative to the center of the face. The inner ring vertices are colored normally. The second callback is for specifying the vertex attributes of the center vertex in the triangle mesh, as it is likely to differ from the ring vertices. In particular, its position comes from the face centroid, not from any topology vertex position. Once we supply all these details to the dynamic mesh, it will generate one or more mesh objects, which we can easily enumerate and add to our scene, using the supplied prefab as a basis. We will nest it under the tutorial object itself. But we haven't yet created that prefab, so let's do so now. The prefab's main functionality will be to provide a material, and for that we'll also need a shader. Our mesh doesn't have any UV map texture data, in contrast to the built-in shaders, but does have vertex colors which aren't handled by the default surface shaders. So we'll modify a basic surface shader by ripping out the texture and UV references and adding a vertex color instead. We can then pull our albedo color from the vertices instead of the texture. Likewise for the alpha. From here, creating a material and assigning our custom shader is simple. Creating the prefab requires a mesh filter component and a mesh renderer component, with the material assigned to the mesh renderer. Now we can save off our prefab and assign it to our tutorial component. Just about ready to see what we've made so far. Let's first tweak the camera to give us a good angle, and then we can play the scene. And there we are, our hex grid rendered with a soft blue and a nice border, with the vertex normals catching the light. From here, it's time to add some interactivity. We'll start with basic mouse clicking. First, we'll use a different color to indicate which face is being pressed. And since we'll be changing the appearance of the triangle mesh, we'll need to remember triangulation strategies for rebuilding the mesh whenever such changes occur. One for the normal state and another for our new pressed state. We'll also need to remember which face received the initial mouse button down event, which becomes relevant when we click and drag instead of click and release. In the awake function, we can assign the two triangulation fields so that we can use them later during runtime. The first looks very much like what we're already doing in the start function when constructing the dynamic mesh for the first time, except that it sets fewer properties. For the outermost vertex, notice that it does nothing at all, advancing to the next vertex immediately. This is because the position, normal, and color will all be guaranteed to remain constant, no need to update them. The inner ring vertex, on the other hand, will set the normal and color because, as we'll see in a moment, the press state might have altered those attributes from their original value. Likewise, the center vertex needs to reset its color attribute also, but its position and normal remain constant. The press state triangulation sets the exact same fields, but we now have a new formula for calculating the normal, and we use the new pressed color also. To get mouse events, we might normally use the input.getMouseDown button function in the update function, or implement the pointer handler interface from the event system namespace. But for convenience, we can use a spatial partitioning picker component from the tile-based worlds framework. This component will consume mouse events, analyze them with the help of a spatial data structure describing the topology, and will raise its own events with data about the involved topology faces rather than mouse position information. We should add that component now. Note that it has three events to be handled. Pick start for when a mouse press begins on a face with a specified mouse button. Pick change for when the mouse is dragged to another face while some button is being held down. Pick end when a mouse button is finally released while over the specified face. We are going to assign event handlers from our tutorial script, so we set those references. The picker component includes a few basic event handlers that can be chosen for debugging purposes. These simply log out information about each event to the console panel, but we'll go ahead and immediately define our actual event handlers. As described a moment ago, the pick start event handler is given the face that the mouse is over when the mouse button is pressed, along with which button was pressed. The pick change handler indicates which face the mouse was previously over and which one it is now over whenever this changes. Finally, the pick end handler is given the face that the mouse is over when a previously pressed mouse button is released and which button that was. We'll create a few helper functions to assist in updating the dynamic mesh based on the pick state. One to revert the mesh back to its original style, ignoring any ongoing mouse interactions, and another to apply custom styling for the current pick state. During pick start, we'll only handle events when the first mouse button is pressed over an internal face, and we'll remember that initial face. Drawing the pick state at this point consists in validating that our mouse is currently hovering over the initial face, and then telling the dynamic mesh to rebuild just that face using the pressed state triangulation. This doesn't immediately update the actual renderable mesh data, however. It only caches the change, letting us alter as many or few faces as we wish. To finalize the changes, we rebuild the mesh, specifying which attributes have changed. This will intelligently update only the data necessary, and only for submeshes which changed. The pick change event is simple, clearing the old state and re-rendering the new state. And the pick end event only clears the old state and the initial face that we had clicked on previously. Now that we've defined these event handlers, we can hook them up in the inspector. Now we're ready to see some more progress. Et voila! The face becomes red when we click on it, reverts to blue when we mouse off, and back to red when we hover back, and back to blue again when we release the mouse button. That level of interactivity is already enough for a lot of purposes, but let's spice things up with some pathfinding. As before, when adding a pressed state, we'll define a customizable color field, and a triangulation for building faces that are a part of an actively rendered path. We'll also keep track of a Pathfinder object and whatever path it has found. We'll keep the Pathfinder object itself around so that its memory resources can be reused. The path itself describes the edges between the consecutive faces in the path, which can in some cases provide more useful information that would otherwise be lacking if we just stored the faces themselves. We'll render the path faces pretty much just like the pressed faces, but with a distinct color. We'll also initialize our pathfinder within the awake function. With all of that setup defined, we're ready to take path into account during our mouse events. In the change event, if we're currently hovering over the initial face, or over an external face, which is any area outside of the actual hexagonal tiles, then we clear any path we may have previously calculated. Otherwise, we search for a path between the initial and current faces. Now the A-star algorithm needs to compute both an estimate from any location to the target, as well as the actual cost between two adjacent locations. For flexibility, these can be provided as customizable delegates, which we will supply. The cost heuristic returns positive infinity if either the source or target is outside the hexagonal tiles, essentially saying that it is impossible to find a path between these two locations. Otherwise, it calculates the standard Euclidean distance between the centroids of the two faces as an estimate of the distance. The actual cost between two adjacent faces in this example will be exactly 1, though if the edge is one that leads to an external face, an infinite cost is returned, indicating that it is impassable. Finishing up the event handling, once we release the mouse button, we need to clear the path if one had been previously found. Finally, on to rendering the path. When clearing the pick state, if there is no path or it is empty, we rebuild the initial face as we already had been doing. If there is a path, however, we use the asFacePath function to get the faces of the path rather than the edges, iterate over them, and rebuild each one. Drawing the current pick state is similar. We have a relevant path, we iterate over the faces, but this time we used a path triangulation to rebuild each face. Let's take the path finding for a spin. Sure enough, works like a charm. Except it's rather boring, finding more or less a straight path every time, because there's nothing getting in the way. We should add some obstacles. Even better is if we can create those obstacles at runtime. As with earlier changes, we'll start by adding a color field for blocked faces. We'll also add a custom Boolean face attribute which will store the block state for each face. We'll need one last triangulation to account for the color and normals of blocked faces. As a small tweak, we'll make the normal deviate from straight up much more significantly so that blocked faces stand out prominently. Within our start function where we initialize the spatial attributes, we'll also create our new Boolean attribute, wrapping a raw array as a face attribute as we did with vertex positions. It will default to all false, meaning that no face is blocked. Now let's do stuff with these block states. When considering whether to compute a new path, we should clear out the path completely not only if the existing conditions are true, but now also if either the starting or target face is blocked. We'll alter our block states in the pickEnd handler. If we end our mouse click on the same face where we started, let's clear the block state of faces near that face. Otherwise, let's block all faces along the current path, if there is a valid path. We'll write these two functions in a moment. One last use of the block state is naturally in the pathfinding cost function. If the target face is blocked, that's another reason to return positive infinity to indicate that it is impassable. Here's the implementation for blocking faces in a path. Just like with our path rendering, we iterate over each face in the path, set the block state to true, and rebuild the face in the dynamic mesh. To clear blocked faces within the vicinity of a particular face, first we'll clear and rebuild the face indicated. Then we'll make use of the face visitation utility class. This class contains numerous functions for visiting connected faces in a variety of ways, flexibly handling the order in which faces are visited, as well as the conditions for when visitation should stop. In this case, we'll perform a breadth-first visitation of connected faces, measuring depth from the initial face. We supply a delegate that is called each time a face is visited. We're given the visited face itself, naturally, the depth from the initial face, and a biref parameter letting us control the visitation state. For each visited face, if it is currently blocked, we clear its block state and rebuild the triangle mesh for that face. We then check the depth. If we've gone as deep as we intend to go, then we set the state to discontinue. Other faces in the queue to visit will still be visited, but this face will add no additional adjacent faces to the queue. We'll add clear radius as a public field so we can set it from the inspector. We should be good to go at this point. Let's run it. Here's our path, as before. And now when we release the mouse, we get a persistent line of blocked faces. If we try to path across this line, our path now needs to go around it, rather than through. If we just click and release, all faces within 2 steps from the clicked face are successfully cleared. And increasing that to 4 enlarges the cleared area as would be expected. And that's it for this tutorial. Thanks for watching, and hopefully this has given you a taste of what you can do with the Tile-Based Worlds framework and how to do it. Once again, the Tile-Based Worlds framework is available on the Unity Asset Store. This is version 1.0, already quite powerful and flexible, but there's plenty more that I aim to do with it. All feedback is very welcome, either here in the comments, at the Unity Asset Store or the Unity Forums thread listed in the description, or on my own blog at experilist.com. Thanks again, and happy world building!